Good morning, everyone. My name is Carlos Moreno, and I'm here today representing a collaborative research effort from the Central University of Venezuela, San Longowo Institute of Engineering and Technology in India, and Jacksonville State University in the US. We are delighted to present our work at the Modern Systems 2025 conference within the METAIOT special track. Our presentation is titled Development of a WebRTC-based video calling application to predict quality of service patterns using an artificial neural network. My most relevant background includes a PhD in telecommunications and informatics from Telecom Sud Paris, jointly with the University Paris 6, Pierre and Marie Curie in 2009, and a postdoctoral research fellowship funded by the Caroline Foundation of Spain at the Polytechnic University of Madrid in 2022. I also earned a master's degree in Big Data and Business Intelligence from Next Educación and University Isabel I. I earned an MBA specialization and master's degree on data networks and undergraduate in electronic engineering from Venezuela. My team is composed by engineer Ezequiel Frias, who is a former student and skilled developer specialized in Python, JavaScript, artificial intelligence. My colleague, Dr. Vinod Kumar Verma, an expert in big data, the Internet of Things, and trustworthiness. And my colleague, Dr. Eric Games, a specialist in data networks, including IPv6, cybersecurity, software-defined networking, vehicular ad hoc networks, VANET, and SCADA systems. Here is the outline for today's talk. We will begin by discussing the motivation behind integrating artificial intelligence into real-time communications, followed by a review of the state of the art. We will then formalize our problem statements and research questions. The core of the presentation will cover our methodology, focusing on scenario establishment, neural network development, and prediction testing. Finally, we will analyze the results across 4 distinct network environments and present our conclusions and future work. Real-time communications has evolved significantly over the past few decades. We moved from early peer-to-peer technologies through structured protocols like SIP to the emergence of web real-time communication, or WebRTC. WebRTC is an efficient open-source technology that enables real-time peer-to-peer audio, video, and data transmission directly between browsers, eliminating the need for plugins or external software. It's now a cornerstone of modern decentralized communication systems. Due to its inherent low latency, WebRTC has revolutionized platforms like Google Meet, live streaming in general, and voice over IP services. The standardization of WebRTC APIs by 2021 underscored its permanence and versatility. Simultaneously, the application of artificial intelligence in video communications has rapidly advanced, moving from basic supervised machine learning techniques like linear regression, SVM, to deep learning architectures, notably convolutional and recurrent neural networks, CNNs, and LSTM. This transition addresses critical quality of service indicators, such as jitter, latency, and packet loss, as well as quality of experience. Metrics like mean opinion score or MOS, PSNR, SSIM. The challenge lies in developing applications with advanced capabilities to predict quality of service patterns. Predictive analytics are crucial because they enable a proactive shift from reactive network management to anticipatory optimization, allowing corrections before users perceive degradation. We aim to contribute specifically to this deep learning phase by integrating advanced neural networks models directly into a WebRTC application. At this time, there's a lot of work going on with reinforcement learning, hybrid models, dynamic adaptation of WebRTC. There are some experimental models related to attention and transformers. Research utilizing machine learning with WebRTC is growing. The study of quality of service prediction using AI is well established. Prior work has used various machine learning models, including isolation forest and XGBoost for anomaly detection in network traffic. Other research successfully applied artificial neural networks for failure prediction in IP networks. Critically, advanced models incorporating recurrent neural networks such as the topology-aware QoS GRNN or TAQ GRNN and models predicting multivariate time series voice over IP metrics have demonstrated high accuracy and in capturing temporal dependencies. However, many of these foundational works, while impactful, do not specifically consider WebRTC as the base technology. Our work distinguishes itself by developing an architecture explicitly from predicting quality of service in interactive WebRTC video calls rather than general streaming or legacy voice over IP systems. Some other works in non-WebRTC have studied content-aware network traffic predictions dynamically, online multimedia traffic classification, and deep learning models for service quality of service prediction based on feature mapping and inference. Research utilizing machine learning within WebRTC is growing. For instance, industry leaders like Google have deployed machine learning-based bandwidth estimation, BWE, systems that leverage a combination of LSTM and dense layer architectures to process real-time statistics. This approach significantly reduces negative parameters like video freezes. Other studies have successfully used deep neural network, DNN, to create no reference quality of experience models based solely on WebRTC client statistics, such as jitter and bandwidth. These works confirm that the WebRTC client statistics provided via APIs are viable source for deep learning models. Our specific contribution builds on this foundation by designing a model intended for proactive quality of service prediction across varied degradation scenarios. Given the critical role of quality of service in ensuring an optimal user experience in video calls, our research was designed to address two primary questions. First, which quality of service metrics can be considered to measure, analyze, and predict quality of service patterns? We focus on key indicators critical to user perceived quality, latency, jitter, and packet loss. Second, which specific type of neural networks predict quality of service better in WebRTC-based video call. To answer this, we systematically evaluated 4 recurrent neural network architectures. This study was conducted in collaboration across our universities, leveraging expertise in big data and AI architectures. Regarding the methodology, description of scenarios, the test bed. Our methodology began by identifying 3 critical quality of service parameters in WebRTC: latency, jitter, and packet loss rate. The client with the network link conditioner tool on the left side is connected to the internet via simple fiber provider using the 400 megabits per second fiber optic WAN access link. Internally, the wireless LAN connection is established through a Wi-Fi 5 network operating on the 5 GHz band with the 80 MHz channel width. On the other hand, at the right side, the remote client is connected to the internet via the Net Uno provider, also through a fiber optic link with the bandwidth of 200 megabits per second. In its wireless LAN, Wi-Fi 5 is also used on the 5 GHz band with the 80 MHz channel width. WebRTC has been developed and has been implemented over these scenarios. We use WebRTC clients by using React, JavaScript, and the libraries Peer.js. And regarding the server, we use Node.js and Socket.io. Based on the ITUT G1010 recommendation, we established 4 representative scenarios to validate the solution. Scenario 1, acceptable quality. Scenario 2, moderate degradation. Scenario 3, critical quality. Scenario 4, extreme conditions. As we can see on this table, from top to down, the bandwidth is decreased from 50 megabits per second to 0.3 megabits per second. The latency is increased from 20 milliseconds to 500 milliseconds. And packet loss rate, or PLR, is increased from 0% to 20%. Regarding the architecture of the neural network, we can say that for the analysis of patterns and the prediction of network conditions based on the collected metrics, it was decided to implement an RNN, recurrent neural network, formed by 4 layers. One RNN input layer receiving the 6 quality of service metric values, one RNN layer, one dense layer, and one output reshape that redimensions the dense layer, outputting the 6 predicted quality of service metric values. We had these 6 indicators: latency, jitter, and packet loss for video, and latency and jitter and packet loss audio. These 3 for audio. So we had 6 indicators. We implemented a recurrent neural network architecture, which is inherently designed to handle sequential time series data like quality of service metrics. The network consisted of 4 layers, as we said before, but an input layer, an RNN layer, either GRU or LSTM, a dense layer, and an output reshape layer. To find the optimal model, we conducted a robust comparative methodology. evaluating for experimental configurations based on the cell type, gated recurrent unit group, and long short-term memory LSTM, and the prediction approach, single output versus multiple outputs, multiple step. The models were trained on a general dataset encompassing all 4 scenarios during 1 hour approximately, with 80%, and were applied to 20%, one call of 5 minutes per scenario. We can see here the t-stable, the hyperparameters in each case. As we are going to explain on next slide, the LSTM was the best architecture. Our evaluation focused on mean absolute error, MAE, mean squared error, MSE, and root mean squared error, RMSE. While single output models, specifically LSTM1, achieved the lowest error metrics, MAE, of 0.0601, they presented significant limitations for long-term prediction, including cumulative error propagation and high computational inefficiency. Therefore, we prioritize stability and proactive management. A mechanism that was implemented to request a statistical report at 2-second interval by using function getStats. Of course, we use definitely the LSTM architecture. So, in order to capture sudden variation in connection quality that might be overlooked with a longer interval, then based on the data obtained from each sample, structured JSON objects were built and loaded to an Firebase Firestore database non-SQL. A Python code created fills out a pandas data frame with the data loaded and executes pre-processing and transformation. Round-trip time is divided by 2 to get the latency. Packet loss rate is calculated from packet lost and packet received for video and audio separately. We had a collection with documents, and each document had fields. For instance, packet lost, packet received, and round trip time were inside one document. This is the paradigm ELT, extraction, loading, transformation. The multi-output LSTM or LSTM-M architecture demonstrated the best capability for predicting extended series stably, mitigating error accumulation, and reducing inference cost. We selected the LSTM-M, which features a sliding window of 60 historical time steps as input to predict 30 future time steps across 6 quality of service metrics simultaneously. This established a deep learning-based model that can reliably predict future call behavior based on the first few minutes of data. Regarding the results, the model in the scenario 1, if we consider the video in acceptable quality, the model successfully estimated the video latency, closely following the actual signal trend. No significant offsets or error accumulation were observed, demonstrating the model's ability to adapt to stable network conditions. Although the model accurately predicted most video jitter values, an outlier was detected near 500 milliseconds, indicating an anomaly in an otherwise stable network. It can be noted that the video packet loss rate was practically 0 throughout the whole experiment, with the model predicting values close to 0. If we consider the audio, we can say that the audio latency predictions exhibited a high level of agreement with the actual data. The model was able to maintain the trend without notable deviations, validating its ability to model this metric properly in low variability environments. In the case of audio jitter, the audio jitter was predicted with minimal errors, showing highly stable behavior. This reinforces the idea that under ideal conditions, the model was capable of accurately capturing slight fluctuations in audio quality. The audio packet loss rate prediction remained near zero, close to the measured data. Let's pass to the second scenario. In the case of the video, it can be seen that the video latency showed an increase in variability compared to the acceptable quality network scenario. While the model adapted well to average values, it exhibited limitations in predicting sudden latency spikes, which is expected given the less stable nature of the network in this scenario. The video jitter showed greater dispersion than the first scenario. Nevertheless, the model could follow the overall trend through, though with slightly reduced accuracy. This suggests that it can adapt to more dynamic conditions, yet with an increasing margin of error. Regarding the video packet loss rate, figure indicates that the model faced greater difficulties in anticipating the actual pattern due to the intermittent and unpredictable nature of this type of traffic on a congested network. Even so, it managed to represent the overall trend of the fluctuations correctly. If we see the audio behavior, the audio latency model effectively followed the general trend of the data. Although, as with the video latency, discrepancies arose when estimating extreme values, the performance is considered acceptable. The behavior of the audio jitter showed wider fluctuations than in the first scenario. The model maintained an acceptable ability to reflect the direction of changes compared to a stable environment. Figure reveals that the audio packet loss rate exhibited variability similar to that of video, although with lower intensity. The model captured the overall trend adequately, despite occasional discrepancies, demonstrating its adaptability while highlighting limitations in scenarios with irregular loss. Let's pass to the scenario 3 regarding the video. Figure shows a pronounced deviation between the actual video latency values and the model's prediction. Although the model was generally able to follow the trend, differences in absolute values were evident, especially during periods of higher delay. This lack of precision can be attributed to the high baseline latency and the significant network instability. It can be seen that in the case of the video jitter, the model showed relatively stable performance. However, it struggled to replicate certain abrupt peaks present in the actual data. Despite this, the predictions reasonably captured the overall jitter dynamics, demonstrating the model's partial ability to adapt to rapid delay variations under critical conditions. Regarding the video packet loss rate, here, figure indicates that the predictions generally remained close to the actual values. However, fluctuations were observed that the model was unable to predict accurately. Regarding audio in the scenario number 3, similar to the video latency, the audio latency also suffered discrepancies as shown in figure. Although the model reasonably followed the trend, significant deviations were noted at the highest delay peaks. As the audio jitter also exhibited behavior similar to that of video. the model managed to follow the overall trend with faced notable difficulties during sudden changes. This illustrates that while the model can adapt to moderate fluctuations, it has limitations when faced with unstable events. As shown in the figure, the audio packet loss rate exhibited patterns similar to those of video. That is, while the model's predictions generally tracked the actual values, discrepancies emerged, reflecting its difficulty in anticipating abrupt changes. We arrive to the scenario number 4. Considering the video, as can be seen in the figure, the model was able to reasonably follow the behavior of the video latency adequately, reproducing the most significant peaks present in the actual data. Although there are some discrepancies between the real and predicted values, the overall trend was effectively captured. It can be seen that in the case of the video jitter, the model showed a reasonable ability to follow the general signal dynamics. Although with specific differences in the maximum values, the predictions were consistent with the variation patterns, reflecting the model's ability to capture changes in delay instability, even if it didn't achieve millimeter-level accuracy. Regarding the video packet loss rate, figure indicates that the model's predictions showed an average difference of around 2 percentage points compared to the actual data. Now we arrive to the last scenario regarding audio. In contrast with the video latency, the audio latency predictions exhibited a greater deviation from the actual values. Increased dispersion and variability were observed, suggesting that the model has more difficulty adapting to rapid and erratic changes for this metric. Nevertheless, the overall trend was partially maintained, indicating that the model still achieved a coherent structural response. As with the video jitter, reveals that the audio jitter predictions provided an acceptable representation of the signal variations. Although discrepancies occur at the specific moments, especially during the most abrupt peaks, the model managed to represent the underlying behavior of the metric, reaffirming its partial ability to adapt to extreme fluctuations. Similar to the video packet loss rate, the figure shows that the audio packet loss rate predictions reproduce the general structure of the actual signal, albeit with slight offset at certain points. While an exact match was not achieved for all values, the model maintained acceptable coherence in terms of dynamics, correctly capturing the variation pattern in adverse environment. Now, arriving to the conclusion, we can say that, to conclude, our research successfully demonstrated that integrated WebRTC technology and recurrent neural network constitutes a viable and modern alternative for quality of service prediction in video call applications. WebRTC simplifies the development of real-time communication environments with robust measurement capabilities. We found that LSTM-type neural networks are capable of capturing the temporal behavior of key quality of service metrics, latency, jitter, and packet loss rate. The model achieved acceptable accuracy, particularly under stable or moderately degraded conditions, while limitations exist in absolute accuracy under extremely degraded scenarios. The model consistently reflected the general trend of network behavior. One of the most significant contributions of this work is proving that the deep learning model can generate reliable predictions of future behavior simply by analyzing the first few minutes of a call. Furthermore, training the model across multiple network scenarios enhances its robustness, allowing it to generalize better under diverse and fluctuating real-world conditions. This capacity is particularly useful for implementing early warning mechanisms or dynamic adaptation systems that can activate before the communication quality perceptibly degrades for the end user. Now we arrive to the future work. Based on our finding, we propose several avenues for future research. We recommend expanding the dataset to include metrics collected in real production environment, such as mobile networks. We also suggest the inclusion of new metrics, such as throughput and mean opinion score, or MOS, to integrate quality of experience. Implementing the model directly in the production WebRTC application as a real-time predictive model is necessary next step. Finally, further research should explore more complex architectures, such as CNNs, LSTMs, or transformer-based models, and work toward the design of autonomous network management systems capable of automatically adjusting resources based on these predictions. I thank you for your attention. As Albert Einstein once said, the important thing is not to stop questioning. I'm now open to your questions and comments. Please feel free to reach out via email or WhatsApp if you have follow-up inquiries. Thank you very much.